Previously, we separated the web tier from the data tier, allowing us to manage and scale our application servers independently from our databases. We then placed a load balancer in front of the web servers to distribute incoming user traffic evenly across the cluster. To handle read-heavy workloads and provide failover redundancy, we implemented a master-slave database replication model. But despite these hardware additions, this architecture hides a severe inefficiency. We are wasting compute cycles on tasks that should have already been solved. Every time a user requests a popular page, the web tier forces the database to execute the exact same query, retrieve the exact same data from disk, and send the exact same response. Furthermore, because user session data is tied directly to individual servers, trying to scale the web tier horizontally to absorb this load remains a highly frictional and fragile process. True scalability depends on eliminating redundant work, pushing data to the geographic edge, and untangling server state. Look closely at the communication between the web servers and the database replicas. They are frequently processing hundreds of identical requests simultaneously. Imagine thousands of users loading the exact same restaurant profile. The data hasn't changed, but the system treats every request as a brand new problem. Reading that exact same data from a physical disk over and over creates unnecessary latency and puts immense strain on the hardware. We solve this by deploying an in-memory cache layer. Using tools like Redis or Memcached, we place a temporary, highly volatile storage area explicitly between the stateless web tier and the data tier. This allows us to implement a read-through caching strategy. When a user requests data, the web server no longer goes straight to the database. This diagram shows a cache miss. The web server checks the cache, finds nothing, queries the database, stores the response in memory, and returns the data. For every subsequent request, the web server finds the response directly in memory, bypassing the database entirely. Because cache data is stored in memory outside the database, it comes with a strict trade-off. You risk serving outdated or stale information to your users if the original database records change. To defend against data drift, we implement a time-to-live, or TTL, expiration policy. This code snippet shows a Memcached API setting an expiration limit of 3,600 seconds. Setting this expiration limit too short forces the system to repeatedly reload data from the database, negating the speed benefits. Setting it too long guarantees users will see stale data. When the cache's memory inevitably fills up, the system must use an eviction policy. The most common is least recently used, or LRU, which gracefully deletes the oldest accessed items to make room for new ones. Caching trades perfect atomic consistency for massive speed gains, effectively shielding the database from redundant reads. With the database protected, we must shift our architectural focus away from the backend and look outward toward the origin web servers and the users themselves. The next major system bottleneck is the delivery of heavy static files, high-resolution images, CSS, and large JavaScript bundles. If your origin servers are located in California, users in Europe must wait for those heavy files to traverse the globe. The physical distance creates unavoidable geographic latency. Serving these static assets directly from the origin also occupies expensive web server compute power that is better utilized executing dynamic business logic. We resolve this issue by deploying a content delivery network, a globally distributed layer of localized edge servers. This diagram demonstrates the CDN workflow. When a user requests an image, the closest edge node intercepts and fulfills the request from its local cache. If the node lacks the file, it requests it from the origin server, serves it, and stores it locally. CDNs are third-party services that charge for data transfer. Caching infrequently accessed files incurs unnecessary costs and provides no significant performance benefit. When these static files do require rapid updates, developers invalidate the cached file by appending a versioning parameter, like v=2, directly into the asset's URL string. Utilizing the edge removes physical constraints and frees the light tier to execute high-value code. Returning to the core web tier, we need to analyze how the load balancer routes incoming traffic to individual servers. A stateful server remembers client data from one request to the next, saving user session profiles directly onto its local memory drive. As shown here, this forces the load balancer to route a specific user back to the exact same server every single time, an approach known as sticky sessions. This setup is brittle. If server 1 goes offline, user A's session data is lost, and their authentication fails entirely. Adding or removing servers to handle traffic spikes becomes an incredibly complex operation when traffic routing is hard-linked to local session states. To fix this, we transition to a completely stateless web tier. We extract the session data out of local memory and move it into a persistent external shared database. Now, any web server in the cluster can accept an HTTP request from any user and fetch the required state from the shared data store. If a stateless server crashes, the load balancer simply reroutes the user to a healthy server. The session remains perfectly intact. Because the servers hold no unique state, new nodes can spin up and instantly accept traffic based on load, with zero manual configuration. Removing state from the application tier turns horizontal scaling from a fragile balancing act into a predictable, automated infrastructure event. This diagram illustrates our fully optimized architecture. We leveraged the CDN to handle static files, eliminating geographic latency for remote users. We deployed a read-through cache to intercept redundant queries, protecting the primary database from massive loads. And we isolated the session state into a shared NoSQL store, allowing the stateless web tier to scale up and down automatically. Professional system design prioritizes the rigorous elimination of unnecessary back-end work. You do not compute what you can cache, and you do not serve what the edge can deliver. But as traffic scales toward millions of concurrent users, a new bottleneck emerges. This entire architecture still resides within a single data center, and all writes still flow into a single master database. To survive the next level of scale, we will have to implement multi-data center routing, build asynchronous message queues, and begin fracturing the database itself.